In my previous video, I have discussed the Seebeck effect, where a difference in temperature created a potential difference or a thermoelectric EMF. And here in this video, I'll be discussing the Peltier effect, which is just the reverse of the Seebeck effect. That is, here a potential difference will create a temperature difference. In the year 1834, a French scientist named Jean Peltier discovered that when electric current passes through a circuit which consists of two dissimilar metals, heat is evolved at one junction and heat is absorbed at the other junction, and that is what is called the Peltier effect. So, if we take a thermocouple made of copper and iron, and if we now connect a battery here, then current will be flowing from the positive towards the negative terminal of the battery. And here, this is the junction, say I will name it J1, and this is the junction J2. So where the current, this junction J1, where the current flows from iron to the copper, iron towards copper, this junction was found to be liberating heat, so this junction was found to be hot, and the other junction where the current flows from copper towards iron, here it is found that this junction absorbed heat, and so the junction was cold. Okay, so now let us try to understand the reason behind this effect. Okay, we all know that there is a large number of free electrons present inside a metal, or say conductor or semiconductor. So if we join two semiconductors or conductors, for example, I'll take the same example for one is copper, the other is iron. So those free electrons will diffuse from the one side where there is large number of free electrons per unit volume towards the side where there is less number of free electrons per unit volume. Okay, so in the case of copper and iron contains much more number of free electrons per unit volume than copper. So obviously the electrons will diffuse from iron towards copper. Okay, so after diffusion, iron will be left with a positive charge because it has lost those free electrons, and copper will be left with a negative charge because it has gained those extra free electrons. Or we can say that iron is left with a higher potential than copper. Okay, so I will write it here. Iron is at a higher potential, a positive potential, and copper is at a lower or a negative potential. Okay, so now let's get back to some very basic concept. Okay, we all know that electrons which are negatively charged are always attracted by the positive terminal of a battery. This one is the negative terminal, this one is the positive terminal of a battery, and the electrons will be always attracted towards the positive terminal of a battery. And we also know that electric current flows in the reverse direction of the flow of electrons. So electric current flows from positive towards the negative terminal of a battery. Or we can also say that electrons always flows from a lower to a higher potential, and current always flows from a higher to a lower potential. Okay, and we also know that energy of an electron is denoted by E is equal to minus QV. And from this equation it is obvious that when potential will increase, energy will decrease. Okay, so here when the electrons are traveling from a lower to a higher potential, the potential is increasing. So when the potential increases, the energy has to decrease. So let us put this concept here in junction J1. What will happen in the junction J1? The current is flowing from a positive to the negative potential. Okay, so means the current is flowing from a higher to a lower potential. So here in this case, in junction J1, potential is increasing, so the energy has to decrease. The energy decrease implies that energy is being liberated. So when the energy is liberated, this junction will automatically get hot. Okay, so now let's look at the opposite case. Okay, if this is the positive terminal, this is the negative terminal of the battery, and if and make this electron flow in the reverse direction, that is from the positive towards the negative potential, which is not the natural way. Then I have to do some work. I have to put some extra energy in moving the electron from the positive towards the negative side, okay, or from flowing the current from the negative towards the positive side. Or we can say that when electrons flow from higher to lower potential or current flows from lower to high potential, some energy must be given, some energy will be absorbed. So if we put this concept here in junction J2, what's happening? The current is flowing from a lower to a high potential, from a negative to a positive, that is from a lower to a higher potential. So in this junction J2, heat will be absorbed. Heat will be absorbed, so this junction will get cooled. Okay. So, like in Seebeck effect, if I reverse the current flow, if I reverse the direction of the current, the both junction will be interchanged. Okay. So, Peltier effect is also a reversible process like the Seebeck effect. Applications of Peltier effect. Peltier elements are commonly used in consumer products. They're used in cooling electronic components and small instruments. The cooling effect of Peltier heat pumps can be used to extract water from the air in dehumidifiers. The Peltier effect can be used to create a refrigerator that is compact and has no circulating fluid or moving parts. Thermoelectric coolers can be used to cool computer components to keep temperatures within design limits or to maintain stable functioning. A Peltier cooler with a heatsink or water block can cool a chip to well below ambient temperature.